Greg Pasternak from Riverside Life, and today we're going to continue covering more lessons that will help you determine the stream types in the 9 county San Francisco Bay Area using the dichotomous key that we've developed to do that. These are the lessons to aid users to determine stream types in the San Francisco Bay Area. And as always with this series of presentations, I'm going to acknowledge Dr. Jihao Wang, who has been lead analyst in helping me to develop the stream classification. Many people participated in data collection, and this is a 7-institution collaboration funded by the University of California Office of the President through the state of California. In the introductory video for this material, I indicated that there are 5 key indicators of stream type that if you can answer these questions and understand them, then you can do this classification. So far, we've covered the first 2, artificial or natural shape and artificial or natural composition. Now we're going to do the next 2 in one video, the deeply entrenched or not, confined valley or not. What is entrenchment? Entrenchment is a process in which a river has an abundance of water and energy to drive channel change, and it has, relative to that, less sediment coming into that section of a river that can deposit there to maintain the landforms in the state that they were in. So what typically happens is that a river will downcut. So there are a variety of factors that can be at play, but typically, like the riverbed will be able to incise with the energy, the velocity, the shear stress that's induced by the amount of flow coming down. And so when you have urbanization in particular, urbanization can drive this sort of change, like deforestation, intensive agriculture, cows getting into channels. There's a variety of things that can do it. But in urbanization, you get a lot more water because you put concrete all over the land surface. And so now more water runs off into the channel, which means there's more energy and force to do work. And that then creates scour. So on the left is just a drawing, so to speak, or picture of what an entrenched river looks like. You see the valley floor high above, maybe you see a soil layer, and then you see these vertical exposures of what the underlying valley floor was composed of, and then the channel is inset down within there. In contrast to an entrenched river, we could say we have a well-connected river. That means like laterally, the channel and its floodplain are well-connected. So you may still see some small vertical banks, but you typically will have a low-lying bars or floodplain surface well-connected. And then beyond that, there may be a higher surface that could be terraces, or that could be the floodplain, depending on the nature of the river that you've got. But the key here is entrenchment is a vertical incision or downcutting process that disconnects the channel from its historic floodplain. And the more something entrenches, for a while, you get what's called a positive feedback, where entrenchment catches more water. It takes even bigger floods to get out of there. So you have a lot more water held in that incised channel, cutting down, and then eventually widening the banks. Okay, so that's what entrenchment is. So what are some of the concepts to have in mind when you're at a site and you're looking and you're trying to decide if you're seeing entrenchment? First, do you see steep, high banks that limit lateral movement of the channel and access for water to spill out onto the floodplain? Second, you might have narrow valley floors or terraces flanking the incised channel, because if the channel starts to widen and you're in a confined or partially confined valley, the width of the remaining valley floor might be lost because of the evolution of the incising channel. You typically will find in entrenchment that you have reduced frequency of getting water out of the entrenched area, right? Because the channel sits far below the surrounding land, so it takes ever bigger floods to get out. There's many things that can drive entrenchment. Another one we have in Davis, California, for example, is that if you change a downstream river, you re-engineer it in some way, that can then propagate a wave of changes up through the system, such as entrenchment. But increase in discharge, loss of vegetation, like from grazing, channel straightening, or leveeing, dredging. There's a lot of things that can do it. And then, of course, the evolution process that we call urban stream syndrome. And here is again the channel evolution model illustrative of urban stream syndrome, where you start with a relatively small channel set into a floodplain. And then outside of that, you may have terraces or just right onto the valley walls. And you begin with a phase of vertical incision, cutting down through that. And eventually, the banks get so steep for the material that they're composed of, they'll start falling apart and the channel will widen. And it takes ever more water to spill out of that. Eventually, you could get so wide and so deep, you may now begin to create a new, what we call inset floodplain within there with a small channel and a floodplain reestablishing itself down there. That doesn't necessarily mean, I mean, this says stable. I'm not, that's questionable, depends on the setting, because still a high flood will be trapped. So now this is where I've talked about in some of the videos on the Riverside Life channel about that, a gravel bed river in a confined valley functions differently from one in a partially confined or unconfined valley. So you've gone from like an unconfined channel dynamic to ultimately a confined dynamic. So it really is on a process basis quite different and still a significant concern for human activities. I've shown you photos in some of these earlier lessons presentations where you've got like a house right next to a deeply entrenched bank. Well, with a house there, that owner is not going to want to allow their bank to widen and go through this process. So they're going to try to halt this evolution at this stage 2 or at stage 3 to protect their house. It's important, in my opinion, to differentiate confinement versus entrenchment. This isn't something that has been done in the past for some of the systems for entrenchment. So how do you quantify entrenchment? We'll get to that. But one thing I want to differentiate is just because a channel is close to some sort of barrier on the side doesn't mean that that's entrenchment. And so what is confinement and what is entrenchment? So confinement is a measure of how wide the valley is. In this left simple photo of a triangular valley, you've got hillsides on either side, and then a stream is flowing through the bottom. This could be, for example, in our classification, an N1 or an N3 stream. In an N1 stream, you have you're a headwater stream, you have a small amount of water, but when it rains, heavy storm, it's going to be water flowing. You're going to have boulders and colluvium here at the bottom of this valley, and the water is laterally confined by the hillside. That is not entrenchment. It's a different process. A lot of different things are going on here. You may have hillside landsliding processes that are taking place. You've got a very steep river with 10 to 20% slope. A lot of things are going on in that setting. Entrenchment is how far down below the valley floor a channel cuts. So you can't have entrenchment if there's no valley floor. Now, a confined river, which we have defined in California as being 100 meters or less in width for its valley floor, you don't have to have no valley floor to be confined. If it's 100 meters or less, we consider it to be a confined valley. If it's 100 to 1,000 meters wide, we consider it partially confined. And if it's more than 1,000 meters wide, we consider it unconfined. And if you watch the videos as I've gone around the South Central coastal region, the South Fork Eel region, you'll see many examples. I try really hard to get to confined, partially confined, and unconfined channels. So now when we get to entrenchment, you have to have a valley floor with alluvial sediment in it. If you don't have it, you can't entrench. That's otherwise you're an incising confined river. That's fine, but you're eroding into the hillsides and the bedrock. That's a totally different kind of system. In contrast, an entrenched river is where you have a channel that's cutting down into the valley floor. And in brown here, I'm showing these exposed banks. So confined channels often have no valley floor, but they're not entrenched. You can have a confined entrenched case if you're less than 100 meters wide. Okay, so we have been looking at how do you measure and quantify entrenchment, and it's really surprisingly limited for what's out in the scientific literature. The most commonly used metric for entrenchment is something called the entrenchment ratio, which is in a textbook by Roskin. In this ratio, what happens is you have to be able to define something called the bankful channel. And I'm not going to go into a long discussion of what bankful is, but if you can define a bankful channel, then you identify the depth at bankful, you go up another depth high, and then you measure the width of whatever's out there. And then the entrenchment ratio is the width of this flood prone area divided by the width at bankful. That ratio then, if you look at the number of it, the bigger this number actually means the less entrenchment, which I think is idiotic personally. Why would you create a number that tells you the degree of entrenchment, and the bigger the number, the lower the entrenchment? I don't know. Maybe there's some good reason. I don't know. But for me, I would have made a ratio the other way. I would have made it that the bigger the ratio is, the more entrenched it is. In any case, let's look at some of the problems with this. And the glaring problem is, what if there's no bankful channel? For example, for sure, no artificial channel, no human-made channel has a bankful dimension. That is just by definition, sorry, it's no. So all agricultural, we have the ditches, the canals, the bank protected rivers, none of them are going to have a bankful channel. Now, I'll correct that a little bit. Okay, so let's say you have a bank protected river. In that type, the bank protection may be high up on the flood prone area, and maybe you have an inset bankful within there. So I'll allow that. But A1, A2, A3 is naturalizing river, but they typically don't get all the way to that point. Maybe. So A1, A2, A4, A6 are not going to have a bankful channel in them. And so therefore, the entrenchment ratio is useless for use in the Bay Area, because if it doesn't work for all of them, we can't use it. The other problem with this ratio is it doesn't distinguish between confinement and entrenchment. This is not the entrenchment ratio. This is the entrenchment and confinement ratio, because what is the thing that's out here? If you have a confined river and you can somehow determine some sort of bankful, but if you're hitting the valley walls, you are not measuring entrenchment, in my opinion. You're measuring some sort of weird blend between the combination of entrenchment and confinement. And so for these two reasons, the fact that we can't use it in many artificial channels and the fact that it doesn't differentiate confinement from entrenchment means that this is not a technically sound metric for entrenchment. The problem is that what makes this such an attractive metric is that it's non-dimensional, meaning there's no units to it, because you have a length, which is the width at the flood-prone area, divided by another length, so it's non-dimensional. So in other words, a small river in a relatively small valleyway, let's say, flood-prone area, has the same ratio as a big one in a big one, and so the ratio is the same. I don't know that having a non-dimensional value is definitive as important. I mean, a lot of academics get all excited about having it be non-dimensional, but I don't see that as critical, especially when you're in a region. If you're doing something in a global context where you really want to have something independent of place, then it can be really useful. But if you're in a region A region has a scale. I mean, based on the climate, the tectonics that's there, I think you can come up with an absolute number that can be meaningful. How do we assess entrenchment? Well, the first thing is you have to identify where the valley floor is. And I can tell you that with beginners, like there's oftentimes a lack of understanding. Like you're standing in the channel or next to the water's edge, and you look up and you're like, oh well, I see a surface there. That's probably the valley floor. The valley floor is where people live for the most part, so you're going to have houses and factories, and that's where your Home Depot or IKEA or whatever, it's going to be out there. So if you're in an unconfined valley and you're down in some, deeply entrenched river, you can't just look at the inset floodplain and inset terraces, man-made or otherwise. You have to say ultimately, where is that valley floor? It's the highest level, and then you're out onto the valley floor. Once you identify that, then you can measure the height at the valley floor edge. That's a transition from the valley floor into the river quarter. And so we can define entrenchment as the height, the riverbed, like what we call the thawag, which is the lowest elevation in a cross section, to the elevation of the valley floor edge. Now, it may not line up as the same on both sides. I don't think it's going to be so different, but you could always take the lower. I think what we do is we take the average. So, yeah, we take the average between those two. And then the entrenchment is the height between the thawag elevation and that. And typically, we're doing this for 10 cross sections equally spaced along a 200-meter site or something like that. So the first step is finding the valley floor. So let's look at some examples. On the left, here's a partially confined valley. It's less than a kilometer wide. The river is shown as this riparian buffer flowing through what is otherwise a rural to suburban development, this sort of like wildland suburban interface. You can see the valley walls on either side. There's a highway at the toe of one of the valley walls, and the channel is offset from that, except at one point it bumps there. So here's a partially confined valley floor. And then on the right, we have an unconfined valley floor. The valley is so wide here, I'm not even going to try to show it, but typically, like in this case, you've got a deeply entrenched river, and even like this image from Google Earth is showing this sort of dip where the river valley here, not the river valley, the river corridor is at a lower elevation than the valley floor. So these houses are on the valley floor, and then the quarter is inset within that. We have been using an absolute entrenchment metric. In other words, it has a length scale. And we define deeply entrenched, moderately entrenched, or low entrenchment. And we just wanted to be kind of practical, like what's useful for people. You have two choices when you make a metric. One is to do something on a quote process basis. But at this time, we don't have, like, science has neglected absolute entrenchment. We've looked at the literature on incising rivers. They talk about the processes of incision, but they don't really address the absolute value of entrenchment relative to any particular processes. Clearly, more work needs to be done, and hopefully, people who either don't like what we're doing or love what we're doing will all want to go out and do research and answer this for us, or we may have to answer it. But in any case, like on a practical level, which is the other way to define a metric, what's usable by people? We just sort of made the decision, like people tend to be between 5 feet and 6.5 feet tall. And I even like went online and looked, and the average height of women globally is, I think it's something like 5'4" and for men it's 5'7", something like that. But I don't know, somehow you always have a taller friend who's around. So we just decided, well, imagine if you had somebody who's about 6 feet tall and they're standing in the channel, and then what do they see? If they're standing in the channel and the valley floor is lower than the top of your head, we're going to call that low entrenchment. So if it's less than 6 feet tall, about one person height, recognizing that, 6 feet is on the high side. Roughly, if it's less than one person tall, that's very practical for people to do. It's low entrenchment. If it's between 1 to 2 people tall, it's moderately entrenched. And if it is more than 2 people tall, then it's deeply entrenched. We have found this to be very practical. But, let's say you're out there and you're like, I don't know, I can't quite tell. Is it two or more? If it's important to you, bring us a rod. Like they have a telescoping rod. You could get up to 12 feet pretty easily. Have somebody stand on the valley floor, have somebody stand in there, and just see is it more than 12 feet or not. Just be very careful because when you're in a deeply entrenched setting, you don't want to be standing on the bank right on the edge in case the bank collapses under your feet and you could get seriously hurt. So you have to be really careful around these entrenched rivers. But what we've observed is that it's really in the deeply entrenched rivers where urban stream syndrome is definitively driving what's going on. It just doesn't take that much to get to that deeply entrenched. And those rivers really stand out, and there's a lot of them. If you're going to say, for example, what is the priority for management, you wouldn't prioritize a moderately entrenched river unless there was some critical infrastructure there. You would prioritize the deeply entrenched rivers. Our approach has been to develop an absolute metric on a scale of like 1, 2, or more person heights, generally, 6 or 12 feet, as something that is usable. For those of you who are metric, I seriously apologize. I'm so sorry. 12 feet doesn't translate into anything. I checked. I don't know. In the metric system, how tall a person is a number of centimeters that is not pretty easy to have in mind. 6 feet just worked out as sort of convenient for us. Here are some photos of the different kinds of entrenchment settings. These are photos of low entrenchment. So in this middle example, you've got a very small creek on a hillside. It's probably an N1. Yeah, an N1. And so you can see like here, the field person is straddling the creek. Obviously, it's much, much lower than a person height. Similarly, in the upper right, you can see the valley floor out there, and it's less than a single person high. In the upper left, we have a confined steep valley, an N3 river, but the person is standing in the channel. There is no alluvial valley floor. In the bottom left, we have an alluvial floor, but the channel is the entire width of the confined valley. So even though there's alluvial sediment here, this sediment floods annually and is part of, the active channel. But in any case, yeah, so if they were standing up, it's not more than 2 times a person height to get above this active channel height. And same thing kind of in the lower right. Here's another natural river, be an N3, because it's confined. It has a valley floor, but it's relatively a thin, narrow veneer dominated by boulders. So these are low entrenchment examples. Moderate entrenched examples, again, are cases where you may have some bank hardening. You're more than one person high. Here's somebody who's like 6 feet tall. And when you look at the side here, I mean, it's hard to tell from just looking straight at where their head is because of the distances in photographs, but it's definitely more than one person tall, but not more than 2 person tall in all of these photos. You can kind of get a sense of that in this shotcrete photo. With the agricultural ditches, I found it a little bit challenging because, of course, you're not going to go stand in the middle of the mud and figure it out. It's probably private property anyway. So it can be hard to know how deep it is. But like in this photo here, you can go to where maybe there's like a weir structure or some water structure. And at that structure, you can see the bed, and then you can trace the bed either upstream or downstream and have a sense as to how deep it is, or you can always try to reach over with the stadia rod. The deeply entrenched rivers are where it's more than 2 times higher than a person. They really stand out. They're really abundant in a lot of urban settings, especially in the San Francisco Bay Area. And so you'll see a person and The valley floor, like where the homes are, just towers above them. You really want to make sure you're getting all the way out onto the valley floor. And in all these cases, if you're standing in the channel, it's more than two times that height. So we'll stop there, and that gives you insights into valley floor entrenchment as well as confinement, how they're differentiated. If you have any comments or questions, criticisms, whatever it is, you can leave them in the comments. And if you have a photo of a site and you're not sure what to think about it and you want my opinion, you can just send it to me.